Hi. With this video, I'd like to talk for a few minutes about mapping this Monte Carlo concept into our reliability integral formulation we've been thinking about this quarter. I want to make the connection between these two concepts. And hopefully the little cartoon I drew makes sense, but let's get a little bit more mathematical precision and we'll come up with a few formulas that'll be useful as we continue developing this topic. Okay, so we're interested in this general reliability integral, this top equation. This is the one we've been looking at all quarter. And we said, we're going to take an integral of the joint PDF of x over the g of x less than 0 domain, over that failure domain. There's another way to write this, which even for the integrals cases is not bad, but for Monte Carlo is particularly useful. Instead of integrating over a specific domain of x's, I'm going to integrate over all x's, but we're going to put in this, what we call an indicator function. And that indicator function is defined at the bottom of the slide. So it's I indicates that I want this indicator, and an indicator function either evaluates to 1 or 0, and it evaluates to 1 if the argument in the subscript is true, and it evaluates to 0 if the argument in the subscript is false. Okay. So when I've got the subscript that says indicator of g of x less than or equal to 0, I want to say for a particular x, if g of x evaluates to less than or equal to 0, this function is going to be equal to 1. Otherwise, it's going to be equal to 0. So the idea is rather than integrating over only the failure domain, as we do in the top case, we're going to integrate over all x's, but this indicator function is going to equal 0 whenever the limit state function is positive. So over all those x values where the system is safe, this indicator function evaluates to 0, and the integral is not accumulating any values. In the part where the limit state function says we failed, in the g of x less than or equal to 0 domain, that indicator function is a 1, so all we're left with is just the PDF that we're trying to integrate. Okay? So it's just two different ways of evaluating the same function. All right? But that's going to be useful for this Monte Carlo. So now let's say we're going to take samples from this distribution. So we'll take xj, and it's going to be the j independent random sample from the distribution of x. So we're going to generate these xj's with Monte Carlo simulation. And I'll say, okay, for any particular sample of xj, the probability that this indicator function is 1 is the probability that the limit state function indicates a failure, which is the probability that the xj that I sampled is in the failure domain, right? And that's going to happen with probability pf, right? So with probability pf, I'm going to sample a realization of x that causes a failure. That's by definition, right? Pf tells me how likely is it that a realization of x is going to cause a failure. So any particular sample, the jth sample, is going to cause a failure with probability pf. And so the probability of getting an indicator function of 1 is pf. Okay, so it sounds a little circular by definition. We can note that kind of xj causes failure with probability pf. And further, I'm going to make these samples, these xj samples, they're going to be independent of each other, right? So I'll draw a sample. When I go back to draw another sample, it's not going to be conditional on the previous sample or on any other samples, right? I can do that algorithmically. I'll just ensure that each one is independent. And so the values of this indicator function for all of my samples are going to be mutually independent. Okay? So when I draw these xj's and I evaluate this indicator function, I'll get 1s and 0s. I get one with probability pf, and each sample is going to be independent. So these things are a Bernoulli sequence. So Bernoulli sequence is a set of successes and failures, and we get a success with probability p, and each success and failure is mutually independent of all the others, right? So we can take advantage of some of those Bernoulli sequence properties for some of our calculations. Okay, so one last piece to put this together is remember the expectation operator. So we say the expectation of some function h of x, we compute that by taking that h of x function multiplied by the PDF for x and integrating over all x. Traditionally, when you've seen this in basic probability classes like 203, this is written scalar, or we could do the same thing with a vector x. We just have to integrate over the vector of x values. Okay, so let's compare that to this reliability integral rewritten that we just came up with. Right? So I said the probability of failure, we're going to integrate over all x, so that part's the same so far. We've got the PDF for x, same thing as before, so now we just have a joint PDF over a vector x rather than a scalar, but that doesn't conceptually change the calculation. And then I've got this indicator function that I've dropped in there, and that's playing the role of this h of x, right? So h of x was just some function. You put in an x and it gives you out an answer depending on that function. So that's what happens here. We plug in an x, and depending on whether that x causes a failure or not, this indicator function evaluates to a 1 or a 0. So this integral, just by comparing it to the top line, we can see that's equal to expected value of this function. So it's the expected value of this indicator function, right? I'm just doing an expectation operation here, mathematically. Okay? And we can estimate the expectation of a function by getting a bunch of samples of that function and averaging them out, right? So I'll say this PF, I'm going to estimate it. So I'll call it PF hat by estimating the expectation of this indicator function. And so just the average of the indicator function, right? And I could get that by getting a bunch of samples of this indicator function with a bunch of samples of x, and I'll add them all up and divide by n, right? And that's the sample mean, right? Okay, and then the sample mean of a bunch of ones and zeros, I'm going to, out of these n samples, I'll get k of them that are ones and n minus k of them that are zeros. Adding this up is just going to be k, the ones I get, divided by n. Okay, so k is the number of failures where I got a g of x less than or equal to 0, and n is the number of samples. And so that was the 2 over 12 that we saw in the introduction video. So maybe this is overkill to write this all out, but mathematically now we can see the connection of why that's a correct thing to do. We can also see the connection to the reliability integral through these kind of couple steps here. And then finally, k, the number of failures of the system, if that's a count out of a Bernoulli sequence, we can do some statistics on, is this, so I will tell you this is, PF estimate is correct on average, it's unbiased, but we can also see how uncertain are we in this PF depending on how many samples we produce and depending on some other characteristics. So we can explore that a little bit later moving on. But that's the basic idea of the Monte Carlo simulation technique. So we've got the mathematical foundation at this point, and we can try this out in the least basic cases. Okay, so that's it for this video.